Chapter 8, Lesson 3, Acids and Bases. We're on page 232 in our textbook, and on the left-hand side it gives us our objectives. It says that scholars will compare acids and bases and their properties. Scholars will describe particular uses of acids and bases. Scholars will explain how pH is used to describe the strength of an acid or a base. And scholars will describe how acids and bases react when they are brought together. Let's get started. Acids. What makes orange juice, vinegar, dill pickles, and grapefruit tangy? Acids cause a sour taste of these and other foods. Acids are substances that release positively charged hydrogen ions, H+, in water. When an acid mixes with water, the acid dissolves, releasing a hydrogen ion. The hydrogen ion combines with water molecules to form a hydronium ion, as shown in figure 14. Hydronium ions are positively charged and have the formula H3O positive. If you look at the bottom of page 232, you see how that water takes on that extra hydrogen. That's what makes it acidic. Properties of acidic solutions. Sour taste is one of the properties of acidic solutions. The taste allows you to detect the presence of acids in your food. However, even though you can identify acidic solutions by their sour taste, you should never taste anything in the laboratory, and you should never use taste to test the presence of acids in an unknown substance. Many acids can cause serious burns or body tissues. Another property of acidic solutions in that they can conduct electricity. The hydronium ions in an acidic solution can carry the electrical charge and a current. That is why some batteries contain an acid. Acidic solutions also are corrosive, which means they can break down certain substances. Many acids can corrode fabric, skin, and paper. The solutions of some acids also react strongly with certain metals, and the acid-metal reaction forms metallic compounds and hydrogen gas, leaving holes in the metal in the process. I can tell you two stories about how acids can be really, really dangerous. One of my buddies was helping his dad change the battery in their truck, and batteries have acids in them because they're going to conduct electricity and actually produce electricity by the different chemical reactions that happen inside. He pulled the battery out of the vehicle and wasn't careful with it and tipped it on its side right on top of where his foot was, on top of his shoe, and some of the battery acid spilled out of the battery and actually poured onto the top of his foot, and he has about maybe a quarter size or bigger burn on the top of his foot, this huge scar from where it burnt through his shoe and actually burnt the skin on the top of his foot because it was so corrosive and dangerous. I can also tell you a story when I worked for the city of Clintonville. I worked as one of the rec department workers, so we had the job of cleaning the bathrooms in the park, making sure that the park was cleaned up. We had to set up baseball fields, mow the lawn, do the weed whipping, all those type of maintenance things for the summer activities, and one of those was to get the pool ready for the city. The city had a pool. And we had to go and clean out all the scum and all the nasty stuff that had come in there from the wintertime, and we were going to use this really strong hydrochloric acid. But we had to first take that really strong, pure acid and had to put water in it to dilute it because it was way too strong from the get-go. We had to be really careful. We had to wear rubber gloves and all these things because it was so corrosive that if it was spilled, it would actually burn through anything. We didn't know this until we actually were carrying it from the truck that we had loaded it on into the area where the pool was, and we spilled some of it right on the concrete. So this acid in its pure form without any water in it. It actually ate a hole in the concrete. It started to fizzle, and the smoke came out of the concrete. It actually tore a hole right through the concrete, and it ate right through it because it was so strong. So acids in those strong characteristics can be really, really dangerous. That's why we don't want to try and mess with anything. Other times we see acids that are a little bit weaker that are in the foods that we eat. Let's look at some of the uses for acids on page 233. You're probably familiar with many acids. Vinegar, which is used in salad dressing, contains acetic acid. Lemon, limes, oranges have a sour taste because they contain citric acid. Your body needs ascorbic acid, which is vitamin C. Ants that sting inject formic acid into their victim. That's why you feel that pain after you've been stung. Figure 15 shows other products that are made with acids. Sulfuric acid is used in products of fertilizers, steel, paints, and plastics. Acids often are used in batteries because of their solutions conduct electricity. For this reason, it's sometimes referred to as battery acid. Hydrochloric acid, which is known commercially as muriatic acid, is used in the process called pickling. Pickling is a process that removes impurities from the surface of metals. Hydrochloric acid also can be used to clean mortar and brick walls. That's what we were doing to clean the pool. Nitric acid is used in the production of fertilizer dyes and plastics. Acid in the environment. Carbonic acid plays a key role in the formation of caves and stalactites and stalagmites. Carbonic acid is formed when carbon dioxide in soil is dissolved in water. When this acidic solution comes in contact with calcium carbonate or limestone rock, it can dissolve it, eventually carving out a cave into the rock. A similar process occurs when acid rain falls on statues and eats away at the stone, as shown in Figure 16. When the acidic solution drips from the ceiling of the cave, water evaporates and carbon dioxide becomes less soluble, forcing it out of the solution. The solution becomes less acidic and the limestone becomes less soluble, causing it to come out of the solution. These solids form stalactites and stalagmites. If you look on page 234, that's the reference to Figure 16. You visualize what acid does when it's in precipitation, or it's called acid rain. When fossil fuels, such as the production of coal to make electricity at a coal-burning power plant, or the exhaust that comes out of our vehicles, if it's prevalent in a huge high concentration like in big cities, it produces a lot of pollution in those areas where you have that high concentration of that activity. Those fossil fuels are burnt and the exhaust that it's released gets into the atmosphere, and that exhaust mixes with water in the atmosphere and then it rains down. You can see here in the picture that it actually can get into the forest and into the water and hurt things with a slight acidity, and it can actually eat away at statues over a long period of time based on what those statues are made up of. Bases on page 235. People often use ammonia solutions to clean windows and floors. These solutions have different properties from those of acidic solutions. Ammonia is called a base. Bases are substances that can accept hydrogen ions. When bases dissolve in water, some hydrogen ions form the water molecules and attract to the base. A hydrogen atom in the water molecule leaves behind the other hydrogen atom and oxygen atom. This pair of atoms is a negatively charged ion called hydroxide ion. A hydroxide ion has the formula OH negative. Most bases contain a hydroxide ion which is released when the base dissolves in water. For example, sodium hydroxide is a base with the formula NaOH. When NaOH dissolves in water, a sodium ion and the hydroxide ion separate. Properties of basic solutions. Most soaps are bases, so if you think about how soap feels, you can figure out how the properties of basic solutions work. Basic solutions feel slippery, and acids in water solutions taste sour, but bases taste bitter, as you know if you've ever accidentally gotten soap in your mouth. Like acids, bases are corrosive. Bases can cause burns and damage tissue. You should never touch or taste a substance to find out whether it is a base or an acid. Basic solutions contain ions and conduct electricity. Basic solutions are not as reactive with metals as acidic solutions are. The usages of bases. Many uses for bases are shown in Figure 17. You can see down at the bottom of the page some things that you might be familiar with. Antacids for heartburn, different types of cleaners or chalk. Bases give soaps, ammonia, and many other cleaning products some of their useful properties. The hydroxide ions produced by base can interact strongly with certain substances such as dirt and grease. Chalk and oven cleaner are examples of familiar products that contain bases. Your blood is a basic solution as well. Calcium hydroxide, often called lime, is used to mark the lines on athletic fields. It also can be used to treat lawns and gardens that have acidic soil. Sodium hydroxide, known as lye, is a strong base that can cause burns and other health problems. Lye is used to make soap, clean ovens, and unclog drains. How do you tell the difference between an acid and a base? Well, we've got a scale called pH that does that. Let's take a look. You've probably heard of pH balanced shampoo or deodorant, and you might have seen someone test the pH of water in a swimming pool. pH is a measure of how acidic or basic a solution is. The pH scale ranges from 0 to 14. Acidic solutions have pH values below 7. A solution with a pH of 0 is very acidic. Hydrochloric acid, stuff that Mr. Shane was talking about when we were cleaning the pool, can have a pH of 0. That's the stuff that ate right through the concrete. A solution with a pH of 7 is completely neutral, meaning it is neither acidic nor basic. Pure water is neutral. Basic solutions have pH values above 7. A solution with a pH of 14 is very basic. Sodium hydroxide can have a pH of 14. Figure 18 shows some various common substances that fall on the pH scale. So if you look at the bottom of page 236, you can see where some of the acidic and basic solutions that you might be familiar with fall. Milk is slightly acidic, tomatoes are slightly acidic, vinegar, and then soda is slightly acidic. So if you've ever heard your dentist say sip all day you get decay, because that acid can eat away at the enamel on your teeth. On the right hand side, you've got egg whites, baking soda, the different type of cleaning products that are more on the basic side. The pH of a solution is related directly to its concentration of hydronium H3 positive ions and hydroxide OH negative ions. Acidic solutions have more hydronium ions than hydroxide ions, and neutral solutions have an equal number of both of those ions. Basic solutions have more hydroxide ions than hydronium ions. So basically, whichever one of those ions they have more of in terms of water, when they're dissolved in water, is where they get that actual measurement of being acidic or basic. The pH scale is just how we tell if it's acidic or basic. Reading check. In a neutral solution, how do the numbers of hydronium ions and hydroxide ions compare? If it is neutral, then there's the equal amount of both of those types of ions. The pH scale. The pH scale is not a simple linear scale like mass or volume. For example, if one book has a mass of 2 kilograms and a second book has a mass of 1 kilogram, the mass of the first book is twice that of the second. However, a change of pH unit represents a tenfold change. That means it's 10 times more acidic if it goes from one number to the next number on your pH scale. However, a change of 1 pH unit represents a tenfold change in the acidity of the solution. For example, if a solution has a pH of 1 and a second solution has a pH of 2, the first solution is not twice as acidic as the second solution, it's 10 times more acidic. To determine the difference in pH strength, use the following calculation: 10 to the nth power, where n is the difference between pHs. For example, pH of 3 and pH of 1 is 100 times more acidic. So each number that you go down on from 7 to 6, it's 10 times more acidic. From 6 to 5, it's 10 times more acidic. So something with a pH of 5 is actually 100 times more acidic than something with a pH of 7. And it goes on the same way in the acid scale and the base scale. If you move one number, it's 10 times from the previous number, and obviously that increases as you go left and right on your pH scale. The strengths of acids and bases. You've learned that acids give food a sour taste but can also cause burns and damage tissue. The difference between food acids and the acids that can burn you is that they have different strengths. The acids in food are fairly weak acids, while the dangerous acids are strong acids. The strength of an acid is related to how easily the acid separates into ions, or how easily a hydrogen ion is released when the acid dissolves in water. Look at figure 19. In the same concentration, a strong acid like hydrochloric acid forms more hydronium ions in a solution than a weak acid does. Like acetic acid, more hydronium ions means the strong acid solution has a lower pH than the weak acid solution. Similarly, the strength of a base is related to how easily the base separates into ions or how easily a hydroxide ion is released. When the base dissolves in water, the relative strength of some common acids and bases are shown in Table 3. Reading check. What determines the strength of an acid or a base? An acid containing more hydrogen atoms, such as carbonic acid H2CO3, is not necessarily stronger than an acid containing fewer hydrogen atoms, such as nitric acid HNO3. An acid's strength is related to how easily a hydrogen ion separates, not to how many hydrogen atoms it has. For this reason, nitric acid is stronger than carbonic acid. So it's based on the number of ions that separate in that solution when it's dissolved. Indicators. What is a safe way to find out how acidic or basic solution is? Indicators are compounds that react with acids and base solutions and produce certain colors depending on the solution's pH. Because they are different colors at different pHs, indicators can help you determine the pH of a solution. Some indicators, such as litmus are soaked in paper strips. When litmus paper is placed in an acidic solution, it turns red. When placed in a basic solution, litmus paper turns blue. Some indicators can change through a wide range of colors, with each different color appearing at a different pH value. Here's an experiment that you'll probably experience when you get to high school. It's called a titration. In this experiment, you have an unknown substance that is potentially an acid or a base, and then you have a known substance that you're going to add to it. In this, you're going to measure the amount of substance that you have initially, and then you're going to slowly add certain amounts of another substance into it. And when this sample is mixed and it's going to change color, that's going to indicate that it's at a certain pH and tell you, well, this was an acid or this was a base based on how much you've added to it. You'll probably do this type of experiment in high school to show you how do you go about finding with an indicator what an unknown substance is, be either an acid or a base. Obviously, the easiest way is to use litmus paper or pH paper to say, well, how much acid or base is in this, because it'll give you a different color indication. But if you don't have that, here's another experimental way in which to do that. Neutralization. Perhaps you've heard someone complain about heartburn or an upset stomach after eating spicy foods. To feel better, the person might have taken an antacid. Think about the word antacid for a minute. How do antacids work? Ant sounds like anti, and acid Sounds like it's the opposite of acid, so it might be a basic solution trying to neutralize something that's acidic. Heartburn or stomach discomfort is caused by an excess of hydrochloric acid in the stomach. Hydrochloric acid helps break down food you eat, but too much of it can irritate your stomach or digestive tract. An acid product, often made from the base magnesium hydroxide, neutralizes that excess acid. Neutralization is the reaction of an acid with a base. It is called this because the properties of both the acid and base are diminished or neutralized. In most cases, the reaction produces water and salt. Figure 10 illustrates the relative amounts of hydronium and hydroxide ions between pH 0 and pH 14. So if one has H3O and the other one has OH, if you put acids and bases together, it forms H2O, one of those extra hydrogens, and the OH pair back together to form a water molecule, H2O, that then neutralizes itself. If you look at the top of page 239, how does neutralization occur? Recall that every water molecule contains two hydrogen atoms and one oxygen atom. As figure 21 shows, when one hydronium ion reacts with one hydroxide ion, the product is two water molecules. This reaction occurs during acid-basic neutralization. Equal numbers of hydronium ions form the acidic solution, and hydroxide ions from the basic solution react to produce water. Pure water has a pH of 7, which means it is neutral. Therefore, that's how neutralization takes place. Now, let's take our reading and apply it to what we have as our reinforcement for today. Reinforcement section 3, acidic and basic solutions. Use the diagram below to answer questions 1 through 5. Take a look here. You got this molecule with another atom on it, and this molecule with two extra atoms on it, and it's changing into something and something else. Number 1, what common substance is a 3-atom molecule like this? What common substance is a 3-atom molecule like the one in this illustration? In this case, the 3-atom molecule we're referring to is water. You've got two hydrogen atoms and an oxygen atom, and it's changing to form H3O positive. If you remember what H3O positive is from our description on the different types of ions that form from acids and bases, H3O positive is found on page 232, figure 14. That's a hydronium ion. So here we see when something's being dissolved in water, it's forming this acid in this case. Number 2, directions look at the right side of the diagram. Explain what happened to the 2-atom molecule. So here's the 2-atom molecule. What happened here? Looks like it gave up this extra atom, which we've already identified as a hydrogen atom, forming H3O positive. So to describe that properly, we would say it lost a positive ion. That's why it's negative over here without that extra hydrogen attached to it. Number 3, identify the 4-atom ion formed if the ion from the 2-atom molecule is a hydrogen ion. So right here you've got the 4-atom, 1, 2, 3 hydrogens and 1 oxygen. That's again our hydronium ion. 4-atom ion would be a hydronium ion. Number 4, what kind of solution, acid or basic, has been produced? Well, if you've got hydronium ions, we know that those are from acids, so this would be an acidic solution. Number 5, will this solution conduct electricity? Why or why not? Is there a potential for positive and negative charges here? Yep, you've got positive and negative charges, therefore you can have electricity move through them. And yes, we know from our story of Mr. Sheen in batteries, and the battery acid that was spilled, batteries have acid in them that allows the electricity to flow in that solution, which would allow this to be an example of something that conducts electricity as well. Yes, the ions can carry electrical charges in the form of a current. Directions for number 6 through 11. Answer the following questions on the lines provided. Number 6, list 3 properties of acidic solutions. We know that they taste sour. They are conductors of electricity. They're corrosive. They react with certain metals, and when they do, they form hydrogen gas when they react with those metals. That was probably 1, 2, 3, 4 different answers Mr. Shane just gave you. Number 7, list 3 properties of basic solutions. Here, where we're talking about the properties of basic solutions, you're on page 235. We said that bases feel slippery and they taste bitter. They can be corrosive, and they can also conduct electricity. Number 8, which ion increases in concentration when a strong acid is added to water? When acid is added to water, it separates into ions, and we know what acids are. They have hydronium ions. Number 9, which ion increases in concentration when a strong base is added to water? Well, the opposite. In this case, strong bases we know produce the hydroxide ion, which is OH negative. When that's dissolved in water, it produces that OH negative. Hydroxide ion for number 9. Number 10, how are the relative strengths of acids and bases compared? Well, the pH scale is used to compare those strengths of acids and bases, and they measure the amount of hydroxide or hydronium ions in a substance. pH scale is how we would go about comparing those things. 11, name the process that occurs when you drop an antacid tablet into a glass of lemonade. Because lemonade is a citrus fruit, it's got citric acid, and you're going to put an antacid, a base in it. That would be neutralization. When an acid and base react, it forms water. Hope that helps you complete your activity for today, your reading and your reinforcement. God's blessings.